Hey everyone! So, you've probably mastered finding the slope of a simple line in calculus. But have you ever stopped and wondered, how would you find the slope of an entire mountain range? Well, today, we're taking that exact idea and scaling it way up, moving from the simple world of lines into the complex world of landscapes. Let's get into it.
Here's the game plan for today. First, we'll talk about the big challenge of jumping from one dimension to many. Then, we'll introduce the star of the show, the Jacobian matrix, and uncover its incredible superpower. After that, we'll see how it helps us tame really complex functions. And finally, we'll tie all this math back to the amazing real-world tech it makes possible.
All right, part one, from one to many. This is where we realize that going from a flat line to a curvy, complex surface means our trusty old calculus tools, well, they're going to need a serious upgrade.
We're all super comfortable with the equation on the left, right? You've got one input, x, you pop it into a function, and you get one output, y. Simple. But the real world? It's messy. What happens when you have multiple inputs, like x1 and x2, that all interact with each other to produce multiple outputs, like y1 and y2? All of a sudden, a simple slope just doesn't cut it anymore.
Think about it like this. In one dimension, the derivative is just a number. It tells you how much a tiny little piece of the line gets stretched out. But in higher dimensions, a tiny input square can go through a wild transformation. It can get stretched in one direction, squashed in another, and rotated and sheared all at the same time. We need a much more sophisticated tool to describe all of that action. So this is really the central question we're tackling today. How do we find the best flat approximation for a curvy surface at one single point? How do we even define the idea of a derivative when our function is a whole landscape instead of a simple line?
And that brings us to section 2. Meet the Jacobian matrix. The answer to our question is this incredibly powerful tool, built for this exact job. It's called the Jacobian matrix, and you can basically think of it as the derivative, but supercharged for higher dimensions.
Now, the official definition might sound a little dense, but the key phrase here is best linear approximation. See, just like a regular derivative finds the best-fitting line that's tangent to a curve, the Jacobian finds the best-fitting plane that's tangent to a surface. It's the most accurate, flat snapshot you can get of a curvy function at one specific spot.
And when you actually look at the matrix, it's not as scary as it might seem. It's really just a neatly organized grid. Each number inside is a partial derivative, and all that asks is a simple question. If I nudge one input just a tiny bit while keeping everything else still, how much does one of the outputs change? The Jacobian just collects all those answers and puts them in one convenient box.
This is probably my favorite way to get an intuition for it. The Jacobian is like a recipe. It's a precise set of instructions that tells you exactly how a tiny square in your input world gets transformed, stretched, twisted, and warped into a new parallelogram in the output world.
Okay, section 3, the Jacobian superpower. So the matrix tells us how a shape gets twisted and stretched, but here's where things get really cool. Its true power comes from answering a different question, by exactly how much did the area change?
You see, while the matrix holds all the detailed directional information, we can boil its essence down to a single, incredibly useful number, its determinant. This one number gives you the magic scaling factor. It tells you exactly how much an area or volume grows or shrinks after the transformation. And the relationship is beautifully simple. If you start with a tiny square that has an area of 1, the area of the new shape it turns into is just the absolute value of the Jacobian's determinant. So, if the determinant is 3, the area tripled. If it's 0.5, the area got cut in half. It's a direct scaling factor, plain and simple.
This becomes absolutely critical when you're changing coordinate systems in multiple integrals. In fact, you've probably used this without even knowing it. Remember in calculus when you switched to polar coordinates and you always had to add that extra r into your integral? Well, guess what? That r is the determinant of the Jacobian for the Cartesian to polar transformation. This is the universal recipe for finding that correction factor, no matter what coordinate system you're using.
So let's move on to section 4, approximating in higher dimensions. We've used the Jacobian to measure change. Now let's use it to build a stunt double for our function. You know, for those times when the real function is way too complicated to work with, we can create a simpler stand-in using something called the multivariable Taylor series. And just look at how beautifully this mirrors what we already know from single-variable calculus. The best linear approximation is just the function's value at a point, plus the derivative times the distance away from that point. In multiple dimensions, it's the exact same idea. The only thing that changes is we swap out our simple derivative, f prime of a, for our new, more powerful tool, the Jacobian matrix, j of a. It's a perfect upgrade.
So why is this so important? Well, it all comes down to speed and efficiency. Calculating the original complex curvy function over and over can be incredibly slow for a computer, but by swapping it out with its simple, flat, linear approximation, especially when we only care about what's happening in a small area, our calculations become lightning fast.
Okay, final section. Why does any of this matter? This might all feel a bit abstract, but trust me, these mathematical tools are not just for textbooks. They are the hidden engine running inside some of the most advanced technology you and I use every single day.
I mean, just look at the range here. From physics and engineering to computer graphics, machine learning, and even economics, the Jacobian is everywhere. It's a fundamental concept for anyone working with systems that have lots of interconnected moving parts, which, let's be honest, is pretty much every complex system out there.
Let's make it concrete. In robotics, the Jacobian is what translates the rotation of a bunch of joints into the precise final position of the robot's hand. In computer graphics, it's the math that lets you realistically wrap a 2D texture, like dragon scales, onto a curvy 3D model. And in machine learning, it's absolutely essential. It's the core mechanism behind backpropagation, which is how neural networks actually learn and improve.
So, if you take away just one thing today, please let it be this. The Jacobian is like a universal magnifying glass. It lets us zoom in on any point in a messy, curved, nonlinear world and see it as a simple, flat, predictable surface. And once it's flat, we can use the straightforward rules of linear algebra to understand it. It's how we make the complex simple.
And that leaves us with one final thought to chew on. We just saw how the basic idea of a derivative can be scaled up to analyze entire landscapes. So what's a core concept in your own field or your own area of interest that, if you could scale it up, might unlock the solutions to much bigger, more complex problems? Something to think about.